Hey, this is not Presh Talwalkar. A uniform ladder of length L is positioned at an angle theta naught with respect to the wall. The ladder starts to slide down. At what angle does it lose contact with the wall? Pause this video to give this problem a try, and when you're ready, continue watching for the solution. Let's first identify all the forces acting on the ladder. The gravitational force, mg, the normal force, F sub n, and the force of the wall pushing on the ladder, which we'll call F sub w. If we call the height of the ladder's center of mass h, and the distance between the center of mass and the wall x, then we have the following equations of motion. mx double dot equals F sub w, and mh double dot equals F sub n minus mg. What we want to solve for is the angle at which F sub w, or x double dot, equals to 0. But since we don't know what F sub w and F sub n are, we don't have enough information to solve this problem. That's because we are dealing with a rigid body, for which the motion of the center of mass is insufficient. We also need to take into account the rotational motion of the ladder, which is given by this equation. The time derivative of angular momentum equals the torque. The angular momentum is given by the moment of inertia I times theta dot. Since this ladder has uniform density, the moment of inertia around the center of mass, its midpoint, is mass times the length of the ladder L squared divided by 12. So the time derivative of the angular momentum is ml squared over 12 times theta double dot. Now let's figure out the torque. By definition, torque is the cross product of the ith force with the position vector of that force summed over all I. Since all the forces are in the xh plane, we can simplify this expression. Here, the perpendicular symbol in the superscript means the component of the ith force perpendicular to the ladder, and r sub I is the distance from the center point in either direction along the ladder. In our case, there are two forces that contribute to the torque, F sub w and F sub n. I took the positive torque to be in the anticlockwise direction, simply because that's the direction the ladder is rotating. The perpendicular component of F sub n is F sub n sine theta, while the perpendicular component of F sub w is F sub w cosine theta. So finally, we can write this equation like this. We can eliminate F sub w and F sub n. To do this, we multiply the first equation by cosine theta, the second equation by minus sine theta, and the last equation by 2 over L. This gives us the following equations. Now, let's add the three equations together. On the left-hand side, we get this. On the right-hand side, these two terms cancel, as do these terms, leaving only the term mg sine theta. Now we need to express the x double dot and h double dot in terms of theta and its derivative. First, let's go back to our picture of the ladder to figure out what x and h are in terms of theta. From this blue triangle, we see that x is L over 2, the hypotenuse, times sine theta. And from this triangle, we see that h is L over 2 times cosine theta. All we have to do now is take two time derivatives of x and h. Plugging these expressions back into the left-hand side of this equation, we obtain this long expression. Notice, however, that these two terms cancel, while these two terms add up to theta double dot. So the left-hand side of this equation reduces to 2/3 ml theta double dot. we can divide both sides by this factor to make the equation nicer. To obtain an exact solution to theta as a function of time is very difficult, but we can convert this equation into an easier one that involves theta dot as a function of theta. To do that, we use this identity, which allows us to write the first equation like this. Canceling the factor of 1/2 and integrating over theta, we obtain the solution to theta dot squared, where, if you recall, theta naught is the initial angle. To figure out the angle at which the ladder leaves the wall, we need to apply the condition x double dot equals to 0. We have already worked out what x double dot was in terms of theta and its derivatives. So the condition we are looking for is theta double dot cosine theta equals theta dot squared sine theta. We can replace theta double dot with this expression and theta dot squared with this expression, which yield this trigonometric equation. We can cancel some terms to get this simple equation. Finally, moving this term to the other side gives 3/2 cosine theta equals cosine theta naught, or cosine theta equals 3/2 cosine theta naught. So the final answer is theta equals inverse cosine of 2/3 cosine theta naught. This is a remarkable result, as it only depends on the initial angle. It does not depend on the length of the ladder, or its mass, or the gravitational acceleration. But there is another way, a faster way, to obtain this result using conservation of energy. Since the only force that does any work is mg, the initial energy is simply mg h naught, where h naught is the initial height of the ladder's center of mass. The total energy, kinetic plus potential, of the ladder at any moment is given by this expression. This term is the kinetic energy due to the ladder's linear motion, while this term is due to the ladder's rotational motion. This term is the potential energy at given h. According to conservation of energy, E equals E naught. Replacing x dot and h dot with the expressions we derived earlier, we can replace this term with L over 2 squared theta dot squared. Combining these two terms and recalling what the moment of inertia is, we can simplify this term. Inserting the expression for h naught and h in terms of theta, and crossing out some terms, we obtain this equation. This is the same equation we derived earlier using forces. All we have to do now is add the condition x double dot equals 0. Or if you recall, theta double dot cosine theta equals theta dot squared sine theta. We can differentiate this equation to obtain theta double dot equals 3g over 2l sine theta. Plugging that into theta double dot over here and inserting this expression for theta dot squared leads to the same result we obtained earlier. So there you have it, the ladder problem solved. If you like this video, please subscribe. Until next time.